Now question 27. Consider an impedance Z is equal to R plus JX marked with point P in the Smith chart as shown in the figure. The movement of point P along a constant resistance circle in clockwise direction by an angle of 45 degrees is equal to option A, adding an inductance in series with Z. So that question number 27. So option A is correct. What is that? Adding an inductance in series with Z. Actually, on the Smith chart I told going from this location to this location like this, you have to add inductance I told So same question that is. Next one is question number 28. Okay. Okay. Question number 28. A transmission line characteristic impedance Z0 is 75, terminated with an impedance of 50 ohm. So ZL is equal to ZL is equal to 50 ohm. The line length is increased from 0. What will be the locus of the input impedance at the other end? Okay, what that fellow is saying For example, this is the transmission line. We have studied this also already. Now ZL is equal to 50 ohm. Z0 is equal to 75. Okay. Now what he is saying is at the load D is equal to 0, student. Can you tell me what is the impedance of the transmission line at D distance? So at D distance, impedance of the transmission line is Z0 ZL plus JZ0 tan beta D divided by Z0 plus JZL tan beta D. Now at D is equal to 0, this is Z0. Z0 is 50. ZL plus JZ0 tan 0 divided by Z0. Okay, I will write Z0 50 plus JZL tan 0, and here ZL is how much? No, student, print miss is there. Z0 is 75 and this Z0 is 75. Print miss over here. Our ZL is what? 50. A 0 0 ultimately 50 you get. So Z of D is equal to, let me check once again. Z0 is 75, ZL is 50. ये दोनों खत्म हो गया इसलिए सब्स्टिट्यूट नहीं किया. So 75 okay, we got this now. Next, for example, that is the formula. I am doing two substitutions. So at D is equal to lambda by 8 means what? See, at D0 means length of the transmission line is 0. At load I am, length of the transmission line is 0 I have taken. If I take D is equal to lambda by 8 means I am increasing the length of the transmission line. Now for this beta D is equal to 2 pi by lambda into lambda by 8, that is pi by 4. Now Z at D distance lambda by 8, that means I have increased transmission line length. That's what he has asked. First you take 0 length, D0, then you increase the length of the transmission line. Then at other end, you are increasing, first you are at load, you increase the length of the transmission line, you come towards the generator, that is nothing but other end. If you take D is equal to lambda by 8, means assume that this is not there now, this is not there now, only transmission line length is what do you say, lambda by 8. Overall length is lambda by 8 you take, then automatically you are finding impedance at lambda by 8 means this is impedance at other end, that is input end actually. That's what he was asking. So put D is equal to lambda by 8 now, total length. So he is saying the input impedance at other end. That input impedance becomes impedance at other end. Once again I am telling, D0 means at the load. What is the length of the transmission line? 0. Then length is increased. I have taken lambda by 8, that means length is increased. Then what is the impedance locus at other end? Here other end means input only. Now let us calculate that D is equal to lambda by 8. So this is the formula. Z0 he has given as 75. Z0 is 75. Then ZL is what, student? 50 plus JZ0, J75. Tan pi by 4 is 1. Pi by 4 na. So Z0 75 plus J ZL 50 into 1. So if you calculate this now, students, you get this, how you calculate this actually, 75 50 plus J 75 then divided by 75 plus J 50, then 75 minus J 50 multiply with 75 minus J 50. So ultimately we get, after calculation, you can see here, we get a positive reactance. You calculate, you can get that positive reactance you get. Okay, if you want exact value, I have calculated, just a minute. So वो कैलकुलेशन किया हुआ है. This value you get this much, student. If you want the exact value, na, 75 divided by 75 square plus 50 square, then 7500 plus J3125. So you got plus Jx, no, student? Plus Jx means going like this. That is locus B represents that one. Locus B. So in locus B, that type of discussion is there going. So option is option B, locus B. Okay. Next, question number 29. Na? This already discussed in the class. Na? So this is the Smith chart. Then this location R, the central point called Q, this location called P. So what is this location P? P, student, short circuit. What is this Q location? Matched load. Matched load, because I told you gamma is equal to 0 plus J0, then SWR is equal to 1 plus mod gamma divided by 1 minus mod gamma, that is equal to 1. SWR 1 means matched load, that is. So what is this one? This is a open circuit. Open circuit. So option is C. Option is C. Okay. Now here 3 more questions are there. We will solve them. So dear students, here the question number 30. You can see here, there one transmission line is there called length is actually 1 meter. So it is called as a T1 transmission line. This is T1 transmission line. Actually, he has used coaxial cables. Characteristic impedance of this is 50 ohm is given. Now this is input. At input gamma plot is given here. Okay, that means like this grounded means it has two conductors. Input is connected between first and second conductor, output is connected between first and this grounded conductor. That is the meaning of that one. Now here 50 ohm is there, grounded, and here second transmission line T2 is there. So T2 transmission line length is given as capital L. For this also characteristic impedance is 50 ohm, and here it is grounded because all the inputs are connected with respect to this ground. So output is actually open terminal. So this is open terminal. Now this reflection coefficient is there, na? That reflection coefficient, modulus of reflection coefficient versus input frequency. Here input is there, it has some frequency. That frequency is given in gigahertz. So now this waveform is going like this, and here 0 frequency, and he has given this reflection coefficient magnitude is equal to 1, and here it is 0.5, here it is 1. For example, least value of frequency is here. So at f is equal to 1 gigahertz, modulus of gamma is equal to 0. You can see here now, mod gamma is 0 at 1 gigahertz frequency. That means mod gamma is 0 here at 1 gigahertz. So whenever mod gamma is 0 at 1 gigahertz frequency, right? Now mod gamma 0 for input transmission line, gamma is 0 means there is no reflected wave on transmission line. So that means no reflected wave on transmission line T1 because input impedance is 0. So you can understand, student, reflection coefficient is 0 on the transmission line means the load impedance to this one is equal to characteristic impedance, that is 50 ohm. Now the load impedance to this one, I am writing here one or two statements. At the input of T1 mod gamma 0 means T1 is matched. That means ZL of transmission line 1 is equal to Z0, that is equal to 50. So ZL of this should be, what do you say, 50 ohm. Now it is like transistors. This is transistor 1, this is 50 connected load, then this is another transistor. Now for this load impedance is equal to the parallel combination of the input impedance of this, what do you say, the input impedance of this T2, input impedance of T2 and 50, they are parallel, students. Once again I am telling, the output from this one to the output is connected, output of 50 ohm is connected to the input of this one. So let us say the input of this one is having a Z in input impedance of T2 line. Now the parallel combination of these two becomes a load impedance to this one. So this is also is equal to, here ZL of T1 is equal to 50 from this information. Now another information is going on, ZL of T1 is equal to, here ZL of T1 is equal to 50 parallel combination with Zin of T2. So let us say this is equation number. How you got this? From this information. From gamma 0 information you got ZL of T1, load impedance of T1 should be equal to 50. Now you know this is 50 You know this is Zn of T2. From these two, no, you will get ZL of T1 also. From these two you get that is equal to this one. Now how much is required here? How much is required? So this is equation number 2. Put 1 into, that means how much is required here? 50 is required, that is 50 parallel with Zn of T2. Student, here if you want total impedance, how much is required here students? 50 is required. If you want 50, then you make this infinity. If infinity, two paths are there. One path is 50 ohm path, other path is infinity path, then high resistance path. Then this path is preferred. That means overall impedance becomes 50 only. So for this case, Zn of T2 should be infinity. So from this also you get that Zn of T2 if infinity. Tell me 50 ohms parallel combination with 50 ohms parallel combination with infinity gives 50 only. So that's why here Zn of T2 should be 50. So Zn of T2 50 means T2 input is open. So this input is open now. Now you see here, this is also open. That means for which transmission line, if there is a open circuit at output, then same open circuit, comes at input also. That is for lambda by 2 transmission line. So for this, at load open is there. Here also open is required. So that should be T2 should be at input of T2 open circuit and at output of T2 transmission line is open circuit. This comes for lambda by 2 transmission line. That means T2 transmission line length is equal to lambda by 2, that is lambda by 2 is V by F, anywhere he has given V by F into 2. So he might have given that velocity is given as 2 into 10 power 8 in the question. So velocity is given as 2 into 10 to the power 8 divided by frequency we have taken is 1 gigahertz 10 power 9, and this is 2 and this is 0.1 meter you get. So this is the answer. L is equal to length of the second line is equal to 0.1 meter is the answer. Okay. Next 31 question, it is related to the transients. Now 32 will finish and then we will go to 31. So 32 question. Keep reading the information and draw the diagram. A 30-volt battery with zero source resistance is connected to the coaxial line of characteristic impedance 50 ohm. That means coaxial transmission line or otherwise doesn't matter. It is two-way transmission line. So coaxial line. Here how much is connected for this? How much is connected voltage? 30 volt battery is connected, V source or otherwise V generator is 30 volt. The internal impedance of this is actually 0. Here ground connection is given to this one. Okay. The internal impedance of the source is 0. So 30 volt battery with 0 source resistance Zg is 0 is connected to a coaxial line of characteristic impedance Z0 is equal to 50 ohm at t is equal to 0 second and terminated in an unknown load impedance. So here the load impedance ZL is connected. We do not know that value. The line length is such that it takes 400 microseconds from here to here. It takes 400 microseconds for an electromagnetic wave to travel from source end to the load end and vice versa. At t is equal to 400 seconds, that means at t is equal to 400 seconds means at load. The voltage at the load end is found to be 40 volts. then steady state current in amperes through the load is. So that means steady state current you have to find. So he has given total voltage at load is equal to 40 volt he has given. So dear student, what is happening here? Source voltage is 30. That means it is a lossless transmission line, because Z0 is equal to 50 means that is root L by C, then R0, G0, R0, G0, root L by C, it is lossless transmission line. So here he is sending 30 volts, that means 30 volts is going, but here it has become 40 volts. Means what is the meaning of that? Total voltage at load is equal to V plus plus V minus, or otherwise I will do like this, V incident total voltage at load is equal to VL is equal to V incident plus V reflected. So he has given that total voltage at load as 40 volts. Now V incident voltage is nothing but 30 volts only, because if it is going like this, then 30 volts, that is. Now V reflected voltage you can find from this. So reflected voltage is 40 minus 30, and that is 10 volts. Now this is 10 volts. Now you may get doubt that why here 30 volts is there, here 40 volts is there. What is happening in this case? Actually, there is a reflection coefficient. Because of that, reflected voltage is 10 volts, incident voltage is 30 volts. But in this case, at load, reflected voltage and incident voltage, they are in phase. दोनों same phase में है. जोड़ के load में voltage maximum आया हुआ है. That information is given. At load there is a voltage maximum here. So V reflected voltage you got. That means from this gamma is equal to reflected voltage divided by incident voltage, that is equal to gamma value. Reflected voltage is 10, incident voltage 30, 1 by 3 you got. Now what is gamma? Gamma 1 by 3. Gamma is nothing but ZL minus Z0 divided by ZL plus Z0, that is equal to 1 by 3. So ZL minus Z0 is given as 50 here, divided by ZL plus 50 is equal to 1 by 3. So 3 times ZL minus 150 is equal to ZL plus 50. So 2 times ZL is equal to 200. ZL is equal to 100. Now you want load current. Load current is equal to voltage at load. It is like this. How much voltage is going into the load, that is reflected, you should not take. So that means V incident divided by what do you say, ZL. Actually no, I should not write this VL, student. This is total voltage at load 40. Total voltage at load is 40. That has incident voltage and reflected voltage. Out of that, now incident voltage only enters into the load. Reflected voltage without entering, it will come back. So V incident divided by ZL. Then I should write like this, student. Total voltage at load is equal to incident voltage plus reflected voltage, that is given as 40, this one. So from this, this is V incident and V reflected is 10. From that we got this one. Then IL is equal to how much is entering into the load, that is V incident, divided by load voltage, load impedance. Then V incident is 30. 30 divided by ZL is you got 100, that means 0.3 ampere you get. So IL is 0.3 ampere. Actually total voltage at load he has given 40 volts, but out of which 30 volts entering into the load and 10 volts is reflected. For current calculation we should take we should not take reflected one. How much comes into the load current, that is decided by incident one. So this is the answer. 0.3 ampere is the answer. So next one question is there on transients. So dear students, now let us discuss transients on transmission line. Actually, when a pulse generator, that means pulse excitation or otherwise battery, is connected to a transmission line input end, is switched on, then for few microseconds and for few nanoseconds, that means it takes some time to the current and voltage on the transmission line to reach steady values. This transitional period is called as transient. Now that one is basically, you see this one is transmission line first conductor, and this one is transmission line second conductor. Now let us take a total length of the transmission line is L. Now here you are connecting some impedance, here some voltage source Vs is connected here, and otherwise Vg is connected here, generator and generator internal impedance. Okay, this is sometimes it is also called as Zg, or otherwise if you call it as a Vs, then it is Zs, or otherwise if it is pure resistance, Rs also it is called source resistance. Now here you are connecting voltage, here you are connecting load impedance, then this is called Z0, and this is called Z is equal to total length of the transmission line. So this is total length of the transmission line, this one. Now Z0 is the characteristic impedance of this transmission line. Now what happens, students, here? When this switch is turned on, this is the switch actually, at t is equal to 0, switch is turned on. That means at t is equal to 0, switch is turned on, this voltage has not reached the load. So that voltage is at the input end only. Then that voltage experiences only characteristic impedance as a load impedance, because if you want to experience total input impedance of the transmission line, then total signal has to travel along the total length and goes to the load. Then only it experiences the total input impedance of the transmission line. So at t is equal to 0, switch is turned on, the input impedance of the transmission line at t is equal to 0 is Z0, characteristic impedance only. Why are you not experiencing total input impedance of the transmission line? The formula is Z of D is equal to Z0 ZL plus J Z0 tan beta D divided by ZL plus J Z0 Z0 plus J ZL tan beta D. That formula you are not going to use here, because whenever a signal travels for entire length, then only it experiences that much impedance. So at t is equal to 0, switch is turned on. So source, that means Vg, experiences characteristic impedance Z0 as a load. So that means now the equivalent circuit is Zg. Now this is Vg. Here this experiences Z0 impedance. Whatever current is there here, that is called initial current. Whatever voltage is there across, that is called initial voltage, V plus. Now from that V plus is equal to Vg, V plus is equal to Vg, then Z0 divided by Zg plus Z0. Now similarly I plus is equal to Vg divided by total voltage divided by total impedance, Zg plus Z0, amperes, this many amperes. Now if you see here, total time is equal to, actually S is equal to Vt formula that means time is equal to total distance traveled by velocity. So here single trip time, that means single trip time means at t is equal to 0, signal is here, that voltage is called signal. Then after how much time it reaches the load, then answer that time is equal to, single trip time is equal to total length of the transmission line divided by velocity of the transmission line. Here velocity is equal to 1 by root LC if they give, or otherwise root mu or epsilon r is given, then C divided by root mu or epsilon r formula also used. LC given, then 1 by root LC use. Mu r and epsilon r for this medium is given. For example, epsilon r comma mu r of this medium is given. Then you have to use C by root mu r epsilon r formula used. This is phase velocity. Then L by velocity gives single trip time. That is called T1. 1 means for one trip. Then when signal is reflected, again it will take T1 time to come back. Again here mismatch is there. Now I will tell you gamma L is equal to, here I will write gamma L is equal to ZL minus Z0 divided by ZL plus Z0. Now what is happening? At t is equal to 0 you are giving the signal. Now it takes T1 time to reach the load. Then if there is a mismatch at the load, that means gamma L not 0, then signal is reflected. Again how much time it takes to come back here? Again T1 time it takes. Now whenever signal enters here, now this behaves like a load impedance to that. Then reflection coefficient at the generator is equal to, now signal is entering into that behaves like a load for reflected signal. So Zg is the load impedance for the reflected signal minus characteristic impedance is Z0. So that is reflection coefficient at the generator. Now this is, what is this actually? Reflection coefficient at the load, this one. So gamma g is equal to Zg minus Z0 divided by Zg plus Z0. This is nothing but reflection coefficient at the generator, reflection coefficient at the generator. Now already we have seen this is taken as gamma, anyway this is taken as gamma V. For voltages gamma L and gamma G are taken, but already we know that gamma V is equal to minus gamma I, otherwise I will do like this, gamma I is equal to minus of gamma V. That means here gamma I is reflection coefficient of current. So gamma V is a reflection coefficient of voltage. Right. Now let us draw the diagram here. I am taking on this time, on this horizontal axis time, I am taking, okay, we will take this as a distance axis. So this as a time axis. Now let us draw the diagram. I am representing this Z is equal to 0. Now the transmission line length is L here, that much length here, no, that much length. So now here Z is equal to 0, so here Z is equal to L. This is called load end. This is called load end. I will remove this diagram, and this is called load end. This is called source end or otherwise sending end. Okay. So now you draw the line like this, Now this one is time is equal to 0. This one is time is equal to T1. This one little bit equal maintain. Okay. This one is time is equal to 2t1. This one is time is equal to 3t1. Like that it is going on. 4t1. Single trip time, double trip time, triple trip time, like that. One trip means a signal coming from source to load. That is the meaning of one trip. Now, this is actually here also downside is time axis, student. Downside is time axis. This one is actually distance axis. Like this is distance axis. Distance 0, distance is increasing, came to load. So this is also I am drawing like this here, and this is the t is equal to 0 time, and t is equal to t1 time, and this is actually t is equal to t2 time, t is equal to t3 time, that is t1, this is 2t1, this is 3t1, and this is t is equal to 4t1. Now I am asking one question, you answer. What is the time here? Anywhere? 0. What is the time here? t1. What is the time here? 2t1. Second question I am asking. What is the meaning of this distance at the source? What is the meaning of this distance at the mid location of the transmission line? What is the meaning of this distance? You came to the load. Now you have to answer. When I switch on at t is equal to 0 time, then at t is equal to 0 time, at t is equal to 0 time, this one, 0 time, what is the voltage? Answer V plus, initial voltage at t is equal to 0. Initial voltage. V plus means initial voltage at t is equal to 0. I plus means initial current at t is equal to 0. Now, how much time that V plus takes to go to the load? Then answer single trip time. So, if V plus has to reach the load, that means this much. Students, first of all, let me tell you one thing. If I draw a line like this, means distance is increasing. If I draw a line like this, means time is increasing at constant distance. But if I draw a line like this, means time is also increasing, distance also increasing. That is the meaning. Now you tell me here, when a t is equal to 0, voltage is V plus, t is equal to 0, voltage is V plus here at t is equal to 0, voltage is V plus, then how much time it takes to reach load? Answer t1 time. Then in t1 time, how much distance it traveled? L distance. So this is the diagram. Because in the t1 time, this is t1 time, how much distance it traveled? L distance. So what signal traveled? V plus. Now here reflection coefficient at load is gamma L, and reflection coefficient at source end is gamma G. Now I will write here one thing. Gamma L is equal to reflected voltage by incident voltage. Now reflected voltage is equal to gamma L into incident voltage. So gamma L into here, how much voltage is reflected? Then answer, reflected voltage is equal to reflected voltage from load is equal to gamma L into incident voltage. How much is incident voltage now? V plus. So now that much is reflected back. So here, how much is reflected back? Gamma L into V plus is reflected. Then it tries to enter the source impedance. Now वो आदमी नहीं है, उसको मालूम नहीं है कुछ भी, वो ऐसा जा रहा है, उधर लोड मिल गया, वो लोड में जाने के लिए कोशिश, इंपेडेंस मिल गया, वो इंपेडेंस को लोड मान के उसमें जाने के लिए कोशिश करता है. अगर उसका इंपेडेंस ये जेड नॉट इंपेडेंस मैच हो गया, पूरा उसमें चला जाएगा. लेकिन अगर मैच नहीं हुआ और थोड़ा सा रिफ्लेक्ट होता है, उसमें थोड़ा सा जाएगा, थोड़ा सा रिफ्लेक्ट हो जाता है. सो फिर कितना रिफ्लेक्ट होगा इधर? आंसर क्या करना है? कितना रिफ्लेक्ट होगा? आंसर रिफ्लेक्शन कोएफिशिएंट मल्टीप्लाइड विथ इंसिडेंट. सो फिर कितना रिफ्लेक्ट होगा इधर? आंसर इसका reflection coefficient, that is gamma g, I will write here gamma g multiplied with incident, कितना incident आ रहा है, so gamma l into v plus, like this again ऐसा जाएगा वो, so इस तरीके में जाता रहता है students. So here again this is the incident to this and multiplied with gamma l, so gamma g, gamma l square and v plus. This is called voltage bounce diagram. Bounce means reflect. Voltages are being reflected, so it is called voltage bounce diagram. Now you can write voltage equations here. This at this location, actually here v of z comma t, here I will write the meanings. V of 0, z0 and time. What is the meaning? Z0 I have substituted. Z0 means sending end, changing time. So the meaning is voltage, students. V means voltage, Z0 means voltage at sending end with respect to time. If time changes, meaning is that you stay, रुको इधर सोर्स के पास, टाइम देखते रहो, पहले ये गए थे, थोड़ी टाइम के बाद फिर ये आ गया, थोड़ी टाइम के बाद फिर चला गया, थोड़ी टाइम के बाद ये आ गया, उसको ऑब्जर्व करते रहना है. So one example I will write. For example, voltage at sending end, Z0 means voltage at sending end 2T1 plus. Students, 2T1 means this one. 2T1 plus means after 2T1 time. For example, like this. This is 2T1 plus time. ये जो टाइम है 2T1 means this one, 2T1 plus means after 2T1 time. You can see by this time here, you can draw a line like this for your convenience. At this time, you see at this time near the source, this voltage is there, reflected is there, again reflected is there. If you have any doubt, you can if you want, I will tell you one thing. What is the total voltage at the sending end at 2T1 plus time? Then answer this voltage plus the reflected voltage plus again reflected voltage, gamma G, gamma L, V plus. How do you know? If you want, you can draw one line here, and this line is touching this one and this one also, so all of them are present. So the meaning is, at the source at 2T1 plus time, how many bounces came? The incident voltage is there, again one reflected voltage is there, again one reflected voltage is there. Now if you measure voltage at input at 2T1 plus time, then total voltage is sum of first time traveling voltage, reflected, again reflected voltage. That's what you get. Similarly, in that way, you can write here also V of L, that means Z is equal to L I put. Z is equal to L comma T means voltage. Z is equal to T. L means what? Voltage at load end with respect to time. That is the meaning. For example, if I ask you what is V of L comma T1 plus, means what, student? L means at load. T1 is this one. T1 plus means after T1 time. This is called T1 plus time. This one, for example. Not only this one, just beyond this. So now at this time, total voltage is here. Incident voltage is also there. By the time, voltage is also reflected. So both are present. So V plus plus, gamma L and V plus, both are there. Like this, you can write the equations. So this is called voltage bounce. Bounce means reflection. Voltage bounce diagram in transient state. And what is the meaning of current bounce diagram, student? So here I plus will be there, and here minus gamma L comes, minus gamma G comes, because for voltages gamma L, gamma G is taken, and for currents, because at every reversal, current direction is changed. So for example, if incident current is coming like this, that is taken as positive current, then reflected current direction is minus of that, opposite of that. Then reflection coefficient is equal to reflected current by incident current. Reflected current will have opposite sign to the incident current. That is why reflection coefficient of current is taken as negative of the reflection coefficient of voltage. So here minus gamma G minus gamma L should be there. Then here I plus should be there. Then every time here minus gamma L. Here minus gamma G into minus gamma L I plus. Like that it comes. Similar way equations are written. So if you want, I will draw the diagram here. Okay. So that is called current bounds diagram. Current bounds diagram. So that current bounds diagram is similar to voltage bounds diagram. You see this one. This is Z is equal to 0. Now here Z is equal to L. This is load. This is source. And here minus gamma G for currents, minus gamma L for currents. This one is T0. Time axis is taken. Time axis is taken here like this, time. Now this is distance. This one is actually T is equal to T1 time. This one is T is equal to T2 time. This T2 T1 and T is equal to 3T1. Like this it is going on 4T1. Now at the beginning it comes here I plus current. Then it is reflected how much? I plus multiplied with minus gamma L. Okay. Then here again reflected. The reflected one is here reflection coefficient is minus gamma G minus gamma L and I plus. That is nothing but gamma G gamma L minus minus becomes plus. Then again how much reflected student here? Like this. Then you get minus gamma L you have to multiply. Ultimately you have minus gamma G gamma L square I plus. Like this it is. So if anybody asks you what is the here na current at 0 comma t means similar to this one only. Current I of z comma t na, that z distance t time. Current at source end, z0 means source end with respect to time. So for example I of 0 here 2t1 plus means what? 2t1 plus means this time. Here I plus is there, total current, and minus gamma L I plus. Then this one is also there, that is gamma G gamma L I plus is there. So similarly I of L comma T means current at load end with respect to time. That means I of L comma, what do you say, this is T1 time. So I of L comma T1 plus means this value becomes I plus is coming already, but T1 plus time means here you have to take by the time this is reflected also minus of gamma L into I plus. Okay. So this is the equation, students. These are the equations. This is called current bounds diagram. So bounds means reflection. So this is called current bounds diagram. Okay. Now you see this question. This question is given like this. One question is given here. That is question number 30. So this question number 30, no? They are asking you to find load resistance. They have given this information. T is equal to 0, switch is closed. Then RS is equal to 150 ohm. And this voltage is equal to 400 volt. Now there is a transmission line here. The length of the transmission line is 200 meter is given. Then characteristic impedance is actually 50 ohm, and epsilon r is 2.25 given. That means mu r not given, means that mu r is equal to 1 actually. RL is there. Okay. Now that fellow gave here V of 0 comma t, that means voltage at sending end with respect to time, is given t in microsecond, and voltage was 100 volt actually, suddenly decreased and went to 62.5 volt at 2 microsecond. That is the diagram given. Now for this you have to find what do you say, RL. Okay. So here students, gamma L is equal to ZL is not given, so RL minus R naught, that is 50 divided by RL plus 50. That means how can you find RL, student? Find gamma L, then you can find RL. That is the thing. Find RL. So RL is there here. If you find gamma L value, we can find the RL. Now what is gamma G? ZG he has given as RS minus R naught divided by RS plus R naught. So RS is given as 150 minus 50. So 150 plus 50. So ultimately that is equal to, this is 100 by 200. So you get 1 by 2. Now what is V plus, student? If you want, I will draw the equivalent. RS is equal to 150, and this one is Vs is equal to 400 volt. Now at t is equal to 0 time, it experiences characteristic impedance as the input impedance of the transmission line. From this, V plus is equal to Vs divided by Vs into R naught. V plus means here voltage, student, here voltage, plus minus. So I plus means how much current is there. V plus means across this how much voltage is there. So that is the meaning of that one. Okay. V plus means across this how much voltage is there. Now V plus across this is Vs into R naught divided by Rs plus R naught. So Vs is 400. R naught is actually 50 divided by 150 plus 50. This is 200 now. So this is 200. You get to 200 means 2 to 500 volt you get, student, right? Now once if you got this 100 volt, and single trip time is how much, student? Here I will calculate. T1 is equal to velocity by length. So velocity is equal to what is going on? Length by velocity. So length by velocity. S is equal to Vt, no? T is equal to distance by velocity, right? L is how much given? 200 meter. Here it is given, no? 200 meter. Divided by velocity is C by root mu r epsilon r. So 200 divided by 3 into 10 to the power 8. Then root of mu r is 1. Epsilon r is given as 2.25. So 2.25. Ultimately you get this 1 microsecond, student. Okay, 1 microsecond. Then if you see the bounce diagram, 1 microsecond, you see here, this is what then? 2 microsecond means 2 t1 time. T1 is 1 microsecond. This time is equal to 2 t1. 2 t1. All of you, this is 2 t1 time. This one is equal to 2 t1. That means voltage at sending end after 2 t1 time, that means 2 t1 plus is given as 62.5 volt. It is from the diagram. It is from given voltage diagram. Given voltage diagram. That is given actually. Now from the bounce diagram, what is voltage at source end? That means Z is equal to 0 after 2 t1 plus time. Here it is there. This one. This one is that. So that means he has given V plus gamma L into V plus gamma L into gamma G into V plus is equal to 62.5 as given. Now V plus is how much, student? 100 plus gamma L we do not know, we have to find. Then V plus is how much? 100 plus gamma L we do not know. Gamma G is how much? Half. Then V plus is 100 is equal to 62.5. Okay. From this gamma L value you get, that implies gamma L is equal to minus 0.25 you get. Gamma L you got minus 2.5, minus 0.25. Now question solution is over. Gamma L you got, from that you can find RL. So that is the procedure. So I am writing here gamma L is equal to RL minus 50 divided by RL plus 50. This is minus 0.25 is equal to RL minus 50, RL plus 50. This is minus 1 by 4 is equal to component dividend also you can do, student. And minus RL minus 50, 4 RL, 200, this side 5 RL, this side, now this side 150, RL is equal to 150 divided by 5. Any print mistake? Minus 1 by 4, no, that is, yeah. L minus Z naught. So it is fine. This is coming this side, 5. Next, if it goes this side, 150. So, yeah, it is correct now. 5 times, it is 3. Correct, na? So, RL is equal to, yeah, 30 ohms you got. So, this is the answer. Right? 30 ohms is the answer, dear students. Okay. So, dear friends, now let us discuss scattering parameters. Yes, parameters. Scattering parameters. Yes, parameters. Right? Scattering parameters. I am writing one note here. Why that ABCD parameters in network theory, Z parameters, Y parameters, H parameters, hybrid parameters are not useful at high frequencies. What is the reason? Actually, if you want to, you see this one, if you want to measure the Z11, Z11 is equal to V by I1. So here you have to measure the voltage and you have to measure the current. So at high frequencies, voltage measuring equipment at gigahertz frequency, voltage measuring equipment, current measuring equipment not readily available. That too, in electrical circuits and networks, while measuring Z parameters, Y parameters, you need short circuits and open circuits. So it is not possible to achieve these short circuits and open circuits over a broad band of frequencies. Broad band of frequencies means once if you have a microwave circuit, you will be sending different frequencies, in some bandwidth. So it is difficult to achieve short and open circuit conditions for broadband frequencies. And also, for example, we have seen in the transmission line also, for example, here ZG is there, generator, and here you have a tunnel diode, for example, or otherwise power amplifiers, high frequency power amplifiers, or otherwise tunnel diodes, microwave device is there. Now, for measurement purpose, I am doing in the transmission line, for measurement purpose, I am doing here short circuit I am doing, short circuit. Then entire signal is reflected. Then when it enters into the tunnel diode, then it starts giving a different frequency, that is called frequency instability. Sometimes it may burn off. So that is why device goes to unstable mode. So frequently it is very difficult to achieve the stability for microwave active power devices like power amplifier. Here power amplifier means high frequency amplifiers. Here meaning is that and tunnel diodes, etc., etc. So it is difficult to achieve the stability whenever we do short circuiting and open circuiting frequently. Why are you doing short circuiting and open circuiting? If you want to measure the impedance parameters, admittance parameters, H parameters, you have to sometimes make I20, I20 output open circuit. Sometimes you have to make V20, that means output short circuit. So it is very difficult to maintain the stability of the microwave devices. That is why in S parameters, instead of using a total voltage and total current, we use traveling waves as a parameters. Okay. So now let us write these points which I have told you, those points in the note. They can ask this also in objective question. For which of the following reasons network parameters like impedance parameters, admittance parameters, hybrid parameters cannot be used to represent the devices at high frequencies? Whatever I am writing, they are the reasons. Okay. So here, right, if the frequencies are in the microwave range, that is gigahertz frequencies, few gigahertz you say. Okay, few gigahertz microwave range, then impedance parameters, admittance parameters like hybrid parameters, actually they are called network parameters, no student, cannot be measured for the following reasons. Cannot be measured for the following reasons. So first one already I told you, equipment is not readily available to measure total voltages, total voltages, comma, total currents at the ports of the network. At the ports of the network. That means actually students, if you want to measure these parameters, they are like voltage by current ratio, current by current ratio, voltage by voltage ratio, like that. You know, the electrical circuits and network theory parameters. You need to measure the voltages and currents, total voltage and total currents at port 1, port 2, like that. But voltage measuring equipment is available at low frequencies. They give accurate measurements, but at very high frequencies they cannot give the voltage and current values. So that is one problem. Equipment is not readily available. Okay. Second one, I told you, short and open circuits, short circuit and open circuit, short circuit and open circuit are difficult to achieve, over a broad band of frequencies, right? Because once if we design a micro circuit, then we will start sending frequencies in the range of particular bandwidth. So for measurement purpose, you have to do short circuiting and open circuiting. Then I told you it is difficult to achieve these conditions, open circuit and short circuiting conditions, because every time, for example, antenna is there, antenna is there means if you want to open circuit means you remove the antenna, and again if you want short circuit means remove the antenna and again put the short circuit. So it is not that easy. They are very big equipment. It is not that easy to do those things, right? Now, active devices such as power transistors, such as microwave, right? Such as microwave, power transistors, comma, tunnel diodes, frequently will not have stability for short or otherwise open circuit conditions. Actually, they can ask this in objective question, students. Which of the following are the reasons that at very high frequencies network parameters cannot be used to represent the two-port network or n-port network? Then these are the reasons. Equipment not readily available, and over the broadband frequencies difficult to achieve the short circuit and open circuit. I told you example, if very big antenna is there, at load if you want to short circuit, you have to remove the antenna and you have to put the short circuit. It is not that easy. For every time you want to measure something, every time reconnecting the disconnecting and reconnecting is not that easy. Coming to this one, in microwave circuits, active devices like microwave power transistors are there, tunnel diodes, etc. are there. All microwave devices, gun diode, etc. They are all microwave devices, right? And they don't maintain the stability of frequency, and sometimes they burn off also whenever reflected signal enters them. So short circuit and open circuit conditions in the circuit generate the reflected signals. Even though you use impedance matching, but small reflections will be there. But even small reflections can easily disturb the tunnel diodes, gun diodes, etc. Because already at microwave frequencies, no, those devices are very hot actually. We will be cooling them every time. But even small reflections enters into them, they easily go to the instability mode. So these are the reasons. Okay. So that is why S parameters are used to represent the network scattering parameters, right? Now, first point, the scattering parameters of a two-port network, or otherwise simply S parameters of a two-port network are expressed as, so here like this students, B1 B2 is equal to S11 S12 S21 S22 A1 A2 A1 A2 like this. So that means here B1 is equal to S11 A1 plus S12 A2 and B2 is equal to S21 A1 plus S22 A2, dear friends. So you may remember this one or this one, anything you remember, any one of them you remember, student. This is the way they are defined. We will be discussing one by one. Okay, students. Now I am drawing the two-port network here like this. If there is a two-port network here, this box, this box here one wire is there, here one wire is there, like this, in network theory. Inside this box, any device can be there, active device like tunnel diode, otherwise a gun diode, otherwise some power transistor can be there. So this is a two-port network. It is called as a two-port network, for example, right? This is port 1, this is port 2. Now here let us connect some source ZG and VG, like this. We have connected some source here. So this source has generator voltage and internal impedance is there like this. Now it is connected here to the port 1. So this is port 1 actually. Okay, this is port 1. And similarly, some load is there called ZL that is connected to port 2. This is port 2. Now from the port 1, whatever signal from the source, whatever signal entering the port 1, that is called as a incident wave. That is called as a incident wave. So actually high frequency signal symbol, high frequency signal symbol is shown like this, student. For example, voltage is there. Voltage is equal to 5 cos 2 pi 10 power 9 t. That means this is 10 power 9 Hz, 1 gigahertz. Now this voltage waveform, this is, it is called now waveform. The symbol is shown like this. The symbol is shown like this. High frequency voltage waveform or otherwise current waveform, they are called waves actually. Already we have seen in the transmission lines omega t minus beta z. This is the high frequency waveform. For example, radio mirchi signal 98.3 megahertz. So that is high frequency signal. That is also called as a waveform. So high frequency voltages and currents are also called as waves. So the symbol of this voltage, high frequency voltage or current is shown like this. Okay, so here maybe bottom side you can show or top side you can show, doesn't matter, student. So here like this A1 signal is there, that is called incident wave. Now at the port 1, if impedance is matching, that means the input impedance and this ZG are equal, then a total signal enters into the two-port network. If there is no matching here, then something is reflected here. So the reflected signal will go out of the port 1, that is called reflected wave. So B1, this is called B1. So here A1, A2. A1 means incident wave at port 1, A2 means incident wave at port 2, B1 means reflected wave at port 1, B2 means a reflected wave at port 2. So A symbol is used for incident waves and B symbol is used for reflected waves. So similarly, whatever signal coming into the port 2, that is called incident into the port 2, so that is called as A2 here. Sometimes you can show this here also, doesn't matter. You show here or here, same thing. So the symbol, this symbol means a high frequency signal, that is. Now here what do you say, whatever comes out that is called as B2. B2, reflected signal at port 2. Now you may get doubt, how come this incident signal, there is no generator here, how signal enters into the port 2? This is a little complicated discussion. I am explaining, you see. How can A2 signal can enter the port? There are two ways. One way is you connect some source here, voltage source or any source, then because of that source, this signal can enter into the port 2. That is one way. But here that generator, voltage generator is not there. So from that voltage generator, it is not going to enter. Now, what is the reason that this incident wave present at port 2? The answer is, here there is incident wave at port 1. Out of that, something is reflected and something enters into the two-port network. Then when it enters, it travels into the load, that is called as this one. Now again, if there is a mismatch here, ZL, and let us say output impedance is ZO, then reflection coefficient is ZL minus ZO by ZL plus ZO, so that is not 0. Then again something is reflected from here. So if something is reflected because of mismatch at load, now again now freshly that enters as a incident wave at the port 2, because this is not a human being. ये आदमी नहीं है, ये ऐसा रिकॉग्नाइज करता है, ये ऐसा रिकॉग्नाइज नहीं कर सकता है, ये जो है सोर्स से आया, कैसे आया करके, कुछ भी आया इधर, उसको इंसिडेंट सिग्नल मानना पड़ेगा उसको, राइट. So here if there is a mismatch and it doesn't have intelligence, so it cannot recognize from where that signal is coming. So if any mismatch is there, actually here at port 1, whatever signal is coming, that is transmitted into port 2. Now that is shown like this here. Okay, it doesn't mean that the signal comes and bend and come here like this, not like that. Whatever signal transferred to port 1 to port 2, that is shown bottom side, because that is in the direction of reflected wave. That is why. So now if there is a impedance matching, then total signal is received by this, nothing is reflected. If there is a impedance mismatch, so again something is reflected. Now that behaves like a incident signal at port 2. Anyway, we will talk of that later on. One formula is there, you have to remember that formula, students. Okay. Now this is the way you represent the two-port network variables for S parameters. Okay, right? I told you, you can represent them top side also. You can represent this bottom side also. This top side, this bottom side, doesn't matter now. Okay, that is not the issue. Now, the logical variables. लॉजिकल वेरिएबल्स मतलब इधर सही वेरिएबल्स है, सही वेरिएबल्स टोटल वोल्टेज टोटल करंट्स नहीं है, सही वेरिएबल्स होता है, ट्रैवलिंग वेव्स होता है इंस्टेड ऑफ टोटल वोल्टेज एंड टोटल करंट. So the logical variables to use at microwave frequencies are traveling waves instead of otherwise rather than traveling waves rather than total voltages and total currents. So that means logical variable means appropriate variable, suitable variable, that is the meaning. Suitable variables are here at microwave frequencies are traveling waves rather than total voltage and total currents. In this case, what we do, students, we measure microwave powers instead of voltage and currents. We measure microwave powers actually. So at high frequencies, microwave power devices are there. Separately equipment are there to measure the microwave powers at high frequencies, like resistance through the resistance heating method. Different methods are there. They are studied in the microwave engineering. Anyway, that is not there in the syllabus for you. So earlier I was teaching that subject also. Now that is removed from the syllabus. Now I am writing here what is A1. So A1 is incident wave. A1 is incident wave at port 1. Similarly, A2 is incident wave at port 2. Incident wave means the wave means here high frequency signal entering into the port 1, that is the meaning. So here S11, it is modeled, two-port network is modeled in terms of S11, S12, S21, S22. So S matrix, right? And similarly, here B1 is a reflected wave at port 1, is reflected wave at port 1. So B2 is a reflected wave at port 2, students. So A symbol is used for incident waves, B symbol is used for reflected waves, right? And you remember this one, otherwise you may remember this one. So any one of them you remember. So matrix form, you multiply them, you get like this. It is better you remember matrix form. So B1, B2 is equal to S11, S12, S21, S22, A1, A2. Right. Now let us define what is S11, what is S12. For example, student, if you want to define S11 and S21, then you have to make A2 0, student. What is the meaning of A2 0? I told you, if there is a matching at port 2, that means let us say the output impedance of this is ZO, then ZL is equal to ZO, then matching is done, so that no reflected signal, whatever signal goes inside this, that is received by this, nothing is reflected actually. So you have to make A2 0. A2 0 means port 2 is matched. Port 2 is matched. That is the meaning. Impedance matching is done at port 2. So then A2 0 you make, then S11 is equal to B1 by A1. And what is B1? Reflected wave at port 1 divided by incident wave at port 1 is defined as reflection coefficient at port 1. So you can understand that is reflection coefficient only. And similarly, S21 is equal to B2 by A1 provided A2 is equal to 0. That means B2 means what you know? The wave transmitted from port 1 to port 2. So you may confuse here, sir, B2 is reflected wave at port 2. Yes, it is correct. But whenever A2 is absent means there is matching is done, nothing goes here. Now here whatever signal enters that goes to the port 2, whatever signal goes to the port 2, that is shown bottom side in the direction of B2 because the signal going from port 1 to port 2 direction and B2 direction both are same. So now whenever A2 is not there, in that case whatever you send here that goes into the port 2 in the direction of B2, that B2 itself is called as from where that B2 is coming, from the signal what you send at port 2 port 1. So that is why that is called as a transmitted signal from port 1 to port 2. So B2 is called as a transmitted signal from port 1 to port 2 and A1 is incident signal. So that is called a transmission coefficient. So forward transmission coefficient means going from port 1 to port 2. So reverse transmission coefficient means going from port 2 to port 1. That is the meaning. So now let us define S11. So S11 is equal to B1 by A1 provided if A2 is equal to 0. So that means here A2 is equal to 0 means here matching is done in such a way there is no source and matching is also done. Nothing, no signal enters the port 2 here. Okay. So now I am writing here what is the name of B1, dear students. B1 is nothing but reflected wave at port 1 divided by incident wave at port 1. Student, what is the definition of reflected by incident? That is called reflection coefficient. So that is called reflection coefficient at port 1 with port 2 with port 2 matched, right? So that is the meaning, with port 2 matched. That means port 2 matched means A2 0 here na. This is reflection coefficient and A2 0 means with port 2 matched. That is the meaning. Okay. Now this is one thing. Now let us talk of S21. S21 is equal to B2 divided by A1. So B2 divided by A1 if A2 is equal to 0. Now can you tell me what is B2, dear students? B2. Now transmitted, students, if you send some signal here, then from this signal if it is coming some signal coming, then it is called as the reflected signal. But here nothing is there. The signal is coming here in this direction from port 1. That is why it is called as a transmitted signal from port 1 to port 2. So transmitted signal from port 1 to port 2 divided by incident signal at port 1. Now this is called as a transmission coefficient. Transmission forward na. See student, it is going from input to output now, that is why it is called forward. If you see here, it is seen in reverse direction. You have to see in reverse direction. 1 to 2, it is symbolized like that. 1 to 2. That means port 1 to port 2 signal is going. So it is called forward transmission coefficient. Forward transmission coefficient by making A2 0. That means with port 2 matched. With port 2 matched. At port 2 matching is done means there is no reflected wave at port 2. So next definition, student. This is one thing, one parameter, and this is another one. So next go to this one, S12 and S22. For that A1 is to be made 0. That means port 1 is to be matched. So here S12 and S22 we will define. For this purpose, I will draw the diagram there. For this purpose, I will draw the diagram here. Okay. That means for this case you are going to connect the voltage generator at port 2, then only you can send the signal at port 2. Okay, here circuit is done like this. So this is port 1 and this is port 2. Now in this case what do you say, a little bit bigger I will draw. Okay, here generator impedance, here generator is connected voltage generator like this. So here from this whatever signal enters, I told you you can write this top side or bottom side, it doesn't matter, I told you student. So this is A2 and whatever completely enters, then no reflected, little bit reflected because of impedance mismatch, then that is B2 it becomes. Now here is the load. Load is here now, ZL. So if load is here, yes students. Now because of this whatever signal transmitted here, that is shown in the direction of what do you say, B1 here, B1. Now here A10 means, what is the meaning of A10? No signal is entering the port 1. So this is 2-port network. Okay. So no signal is entering the port 1. That means impedance matching is done here. So port 1 is matched now to have A1 value 0. Now you see this one. You want S12 now. S12. So S12 is equal to, S12 is nothing but B1 by A2, provided if A1 is equal to 0. What is B1 now? I told you. Now why here signal is going to the port 1? Because there is a source here. From that source what is coming here? Incident signal at port 2. That means this is the signal which is transferred from port 2 to port 1. So that is called transmitted signal from port 2 to port 1. So transmitted signal from port 2 to port 1. Port 2 to port 1 divided by, what is this A2? Incident signal or otherwise incident wave. Signal or otherwise wave also you can say. Incident wave. Students, signal or otherwise wave both are same. High frequency waveform, that is incident wave at port 2. So this is called reverse transmission coefficient. That means port 2 to port 1. So it is called reverse transmission coefficient with port 1 matched. Port 1 matched means there is no A1 signal here. Now what is S22? S22 is equal to, here you see students, S22 is equal to B2 by A2, A1 is 0. So that is B2 by A2, provided A1 is equal to 0. So what is this B2? So B2 is basically reflected wave at port 2 divided by incident wave at port 2. Okay, that is nothing but reflection coefficient at port 2 with port 1 matched. That means port 1 matched means meaning is A1 is equal to 0. Now, anybody ask you what are the S parameters? Answer, they are reflection and transmission coefficients. It is that simple. If you want to write the decibels, then you have to take 20 log, not 10 log, 20 log, because there I am saying reflection and transmission coefficients. Reflection and transmission coefficients, they are simply ratios of voltages and currents. You have to take 20 log, that is different issue. Then one more point. For example, here S11 is reflection coefficient at port 1, S22 is reflection coefficient at port 2. So diagonal elements in the transmission matrix are reflection coefficients, and other than diagonal elements, they are simply transmission coefficients. That is one point. Now I am going to write the properties of S parameters. For example, we have taken two-port network. For two-port network, this is 2 by 2 square matrix. For n-port network, it is it is a square matrix of order n by n. That is one first point. Second one, for a reciprocal network, like network theory, no need to tell much. For a reciprocal network, S12 is equal to S21. That means in that case, for a reciprocal network, this matrix is symmetric matrix. Symmetric matrix means S matrix transpose is equal to S matrix. This is called symmetric property of the S matrix. Next property, first one is I will be writing them now. You are listening. So first property is it is a square matrix of order n by n for n-port network. Second property is symmetric matrix. That means S transpose is equal to S. That is symmetric matrix. Symmetric matrix it is for reciprocal network. Now S matrix follows. S matrix is unitary matrix. That means S matrix follows unitary property. So what is the meaning of unitary property, students? This is simply called like this, student. It is written like this also. B matrix is equal to S into A also. You can write this one. So like this simply it is shown. B is equal to S into A. Now simply this total matrix is shown with simply S. Simply like this it is shown. Okay. Now unitary follows unitary property means S star. That means complex conjugate of this star means complex conjugate of this transpose, and again take complex conjugate, write rows and take rows and write into the columns, then you get this one. Then multiplied with S matrix gives identity matrix. That is, for example, 2 by 2 1 0 0 1, that one. So that is called unitary property of the S matrix. So S matrix follows unitary property. Next one more is there called zero property. So zero property means the meaning is that zero property of the S matrix, students. I am going to write them after this. Zero property of the S matrix means this is one row, this is another row. Otherwise, this is one column, this is other column. Sum of products of each element, for example, this element, sum of products of each element in any column, that means this column, multiplied with complex conjugate of corresponding term. Corresponding term means this one of other column is equal to 0. That is called zero property. For example, here if you take this column, then you multiply S11. This is one term in this column. The corresponding term is this one in other column. You take complex conjugate of that one, and then similarly you take this one S21, then complex conjugate of this one is equal to 0. That is called zero property of the S matrix. So, dear students, I will tell you few more points in connection with the network theory. S11 is equal to S22. That means input port 1 and port 2 are similar. That means that is why whatever reflection coefficient is there at port 1, same reflection coefficient is there at port 2 means for any network, if now these are not properties, student, these are not the properties, these are the statements. You have solved the S matrix. Then for particular network you have solved the S matrix. Then for that network, if S11 is equal to S22, that means input reflection coefficient is equal to output reflection coefficient. That means port 1 and port 2 behavior is similar. That is why that is called a symmetric network. Now one network is there. For that you found the S matrix. Then you got for that if you got S11 is equal to S22 is equal to 0, you got, that means S11 is 0, S22 is 0. That means port 1 is also matched, port 2 is also matched. So that is the meaning. If both reflection coefficients are 0 means both ports are matched. That is the meaning. Now I have taken one network. For that S parameters are solved. After solving the S parameters, then I got S12 is equal to S21. S12 is equal to S21 means S21 means transmission coefficient from port 1 to port 2. Then S12 means reverse, you have to study transmission coefficient from port 2 to port 1. That is called reverse transmission coefficient. Both are same. That means that is a reciprocal network. So from port 1 to port 2 behavior, if you send from port 2 to port 1 behavior same. So that is called reciprocal network. So next fourth one. I have taken one network. I have solved S parameters. Then I got modulus of S12 is equal to modulus of S21 is equal to 1 I got. What is the meaning of this? 1 means, for example, S12 is equal to, definition is, you can see here S12 definition, B1 by A2. That means whatever is incident here, entire signal is transmitted here. That means there is no loss here. If loss is there, total signal cannot transmit, less value transfers. So that means there is no loss here. So that is the lossless network. Yes or no? And also that means it is 1 means that is lossless network, and S12 is equal to S21 means that is reciprocal also, like this one, reciprocal also. So this is lossless and reciprocal network. Now there are 4 questions here. These are questions. For any network, after solving the S parameters, you got S11 is equal to S22, then that network is symmetric network. So similarly, for any network, after solving the S parameters, you got S11 is equal to S22 is equal to 0. That means for that network, port 1 and port 2 matched. Then for any network, after solving the S matrix, you got S12 is equal to S21. That means it is reciprocal network. Is it a lossless? Nothing can be said because that value is not known to us. So simply it is reciprocal. Now S12 and S21 is equal to 1. Then that means whatever is transmitted at port 1 that reaches port 2 without loss. Similarly, whatever is transmitted at port 2, it reaches port 1 without loss. So that is a lossless network as well as reciprocal. So these points I will be writing in the notes, students. So the diagonal elements are reflection coefficients and other elements are transmission coefficients, students. So students, now let us write the properties of S parameters. So properties of S parameters. Okay. First property, for an n-port network, S matrix is a square matrix of order n by n, right? That is the first point. Second point is S matrix is symmetric matrix, matrix that is Sij is equal to Sji. That means it is like S12 is equal to S21, like that. That is the meaning. That happens, you know, for reciprocal network. So, or otherwise, S transpose is equal to S. So, S matrix is symmetric matrix. That is, this is the meaning for a reciprocal network, right? Third one, S matrix is a unitary matrix. And otherwise you can write like this: S matrix follows unitary property. So like that also you can write. So that means S star transpose multiplied with S gives unit matrix where is unit matrix. So you may get these properties in objective questions. Then so you must say yes, it follows unitary matrix, like that you have to say. So here I am writing example for a two-port lossless network. For a two-port lossless network, S star network, first I will write S matrix. S matrix is equal to S11, S12, S21, S22. Then S star transpose into S is equal to I. Then here S is nothing but S11, S12, S21, S22. Then you take the complex conjugates and take row and write in column wise. So S11 star, S12 star, then S21 star and S22 star is equal to 1 0 0 1. So you can multiply them and then you equate this to 1. For example, S11 star into S11 plus S21 star into S21 is equal to 1. That means modulus of S11 square plus modulus of S21 square is equal to 1. So like that it becomes. Next, fourth one, zero property of S matrix is zero property of S matrix says the sum of products of each term of any column or otherwise this is applicable for row also. If you take column, you have to multiply with other column. If you take row, then you have to multiply with other row. That is the meaning of that. So multiplied by the complex conjugate by the complex conjugate of the corresponding terms of the corresponding terms of any other column of any other column, or if you take any row, then any other row you have to take. Simply in place of column here put row, then here in place of column put row, then again the statement is valid. That means is 0, is sum is 0, student, sum is 0. So that is why it is called 0 property. Okay. Now let us take example. So example, for a two-port network, S matrix is equal to S11, S12, S21, S22. Now 0 property says 0 property of S matrix says, for example, you take this column, student. So S11 multiply with complex conjugate of a corresponding term in other column, that is S12 star plus S21 and S22 star is equal to 0. So that is the meaning of that one, right? Next point, fifth point, for a perfectly matched network, for a perfectly matched network, I told you, if any network is perfectly matched at input as well as output, then all reflection coefficients are 0. That means diagonal elements are 0. So for a perfectly matched network, all the diagonal elements of S matrix are 0. All the diagonal elements of S matrix are 0. That is, reflection coefficients are 0. Then in bracket you write that is reflection coefficients are 0. So now let us write one note. These are all objective questions. For a two-port network, or otherwise for any two-port network, first one, if I told you S11 is equal to S22, if S11 is equal to S22, then that network is symmetric network. Symmetric, that is the objective question. Similarly, another question, if S11 is equal to S22 is equal to 0, then a network is matched at both ports. Then that network is matched at both ports, right? If S12 is equal to S21, then that network is reciprocal. Then that network is reciprocal. Similarly, I told you modulus of S12 is equal to modulus of S21 is equal to 1. That means that is lossless as well as modulus of S12 is equal to modulus of S21 is equal to 1. That means whatever transmitted at port 1 goes to port 2, whatever transmitted at port 2 goes to port 1 without loss, and also it is reciprocal and lossless. So if S12 modulus is equal to S21 is equal to 1, then the network is lossless and matched at both the ports. So then the network is lossless and matched at both the ports. These are objective questions, students, right? Now here I am going to write the formulas, ready-made formulas. Actually those formulas come from derivations. Then how to solve the S parameters for some cases I will write here, right? These are formulas. Actually you have to remember this one. I am taking two-port network. Okay, this is a two-port network, student. Now here this is a port 1 and this is port 2. So this is port 1, this is port 2. Like network variables, na, here I1 current will be there and here I2 current will be there into the port 2, and V1 voltage is there plus minus and V2 voltage is there and plus minus. Okay, you know V1 by I1 is input impedance at port 1, that is called Z1. V2 by I2 is called the input impedance at port 2, that is called Z2. That thing you know. Okay, let it be like that. Just I have represented V1 and I1 here, right? Now I have taken the same two-port network, and this is port 1 actually, this is port 2 actually. So this is port 1, this is port 2. Okay, now I have connected here ZG, VG. Now definitely here if I connect source here means here load should be there, ZL. Because of this something enters here, that is called A1 incident, something is reflected, that is called B1. And similarly here if anything enters that is called as A2. So anyway students, but here with this diagram I am going to explain S11 and S21. So I am going to make it match so that it will not be there. So anyway here it is B2 is there, let it be like this because it is matched now. I want to make A2 0. A2 0 means here nothing is coming means then it is matched. Now here like this if I represent this is I1 and this one is V1 plus minus, and similarly this is I2 and this is V2 plus minus. Now after doing dear students, you know that the matrix is B1 B2 is equal to S11 S12 S21 S22 and this is A1 A2. So that means B1 is nothing but S11 A1, S12 A2, and B2 is nothing but S21 A1 plus S22 A2. Now for example S11 is what students? S11 is equal to B1 by A1 provided A2 is equal to 0. What is the meaning of this one? Port 2 is matched. Now, this is the actual situation. But while deriving the S parameters, what we do, little bit, don't write this one. Here, small correction I will do. This is the actual case. Now, to make A2 0, here some impedance is there. We will call that impedance as R2. This ZL, we will call it as R2. And I can change this by doing some manipulation. So I will take it as a R02. This R2 is terminating like this. No, ZL is terminating impedance at port 2. So similarly, R2 is a terminating impedance at port 2, and this is called reference impedance at port 2. This is a positive value. You can change this. Why you are changing that one? Now in place of ZL, we have put R2. That is R2 means here terminating impedance at port 2. That is we will equate that to reference impedance at port 2. So this is you can change this is positive resistance. Why to change this? So you change this and you connect this one here. That means you connect this one here. That means R2 has become R02. That is called this is terminating impedance at port 2. This is called reference impedance at port 1. So that there is no reflected wave here. There is no reflected wave. So to make A2 0, terminating impedance at port 2 is taken as a reference impedance at port 2. I will write the names also if you want. Now similarly, here this whatever ZG is there, that is taken as a R1. R1. R1 means terminating resistance at port 1. That is called as a R01. That means reference impedance at port 1, that is taken as. So now this is taken as a here no student. For example, VG will have some resistance, students. Let us say some 5 ohm. Then you can connect in series with that 5 ohm some impedance, so that you can change this value. That value we are calling it that as a R1 terminating impedance at port 1. Otherwise, that is also called as what do you say, reference impedance at port 1. So after taking these conditions, we have to do the derivations. Big derivations are there. After doing the derivations, we get this formula Z1 minus R01 divided by Z1 minus R0 plus this is what is this? Reflection coefficient. Already you know S11 is reflection coefficient at port 1. So here Z1 means V1 by I1 input impedance minus from where you are feeding that from this one. So like transmission line, you have any transmission line, then transmission line is there, and what is the reflection coefficient here? ZL minus Z0. What is this Z0? From where you are feeding energy into this. That means from the transmission line having Z0 characteristic impedance, you are feeding energy into this. So ZL minus Z0. Similarly, here input impedance is Z1 and you are feeding energy into the Z1 from the source having impedance R01. So Z1 minus R01 divided by Z1 plus R01. So this is the formula. Using this, we do the derivations and we get the S parameters. You have to remember this one. So here Z1 minus R01, Z1 plus R01, if this one, if A2 0, that means terminating impedance. Student, terminating impedance at port 2 means load impedance at port 2. It is that simple. Now by connecting some resistance in series with that or parallel with that, we can change that value. We change this value in such a way you get R02, that is called reference impedance at port 2. So R2 becomes R02. I will write that also. Okay. And similarly, here S21 is equal to B2 by A1 if A2 is equal to 0, and for that terminating impedance at port 2, that means load impedance at port 2 is equated to reference impedance at port 2. Now this becomes 2 times output side voltage here, port 2 voltage V2 divided by, from where you are sending that, I will call this now as VG1. VG1 means source at port 1. So VG1 under root R1 divided by R2. Of course, this R1 is connected to R01 and R2 is connected to R02. So the terminating impedance at port 1 divided by terminating impedance at port 2. So terminating impedance at port 1, the R1 means that is nothing but source impedance only. If you want, you can change that by connecting some other resistance so that you adjust that value in such a way whatever R01 is required. I will tell you in the solving questions, they give the reference impedance. So for example, they give reference impedance 1 ohm, R01 is 1 ohm is given in the question, so you adjust this impedance in such a way you get 1 ohm. You do something here, source impedance is there. For that source impedance you may connect in series or parallel, you do something in such a way you get 1 ohm there, like that. So anyway, this is the formula if A2 is equal to 0 and what do you say, R2 is equal to R02. So here R2, okay, R2 is terminating impedance at port 2 and R02 is reference impedance at port 2. So now same discussion you can change to this side. Now you connect this source here and this load here, and same discussion comes. That means okay. So I will draw the diagram and I will tell, because simply if I tell you may not understand. Same discussion comes this side also. Similarly here R1 is what, students? R1 is terminating impedance at port 1 is terminating impedance at port 1 at port 1. So R01 is reference impedance at port 1. Actually these are arbitrary positive constants. This one, they are actually arbitrary positive constant. Arbitrary means you can choose them, you can select them. Why to select them? Why to select this? For example, you select this, otherwise you keep changing this in such a way this reflected signal becomes 0. You keep changing this value. Arbitrary means you can select that positive value, that is a positive resistance. You keep changing that until reflected signal becomes 0. That is why at port 2 reference impedance is taken. So they give these values, reference impedance, in the question. Similarly, R01 is also arbitrary positive constant. What is going on here? क्या चल रहा है इधर? If any network is given, if they ask you find the S matrix, then you have to remember this formula. then you have to do the derivation, then you get S11 and S21. I will solve the question so that you will understand. Don't worry about that. So this is how to remember this simply reflection coefficient. This is 2 times of port 2 voltage divided by that voltage is generated from VG1. Then root of R1 near the source impedance divided by terminating resistance at port 2. So similar adjustment you do here like this. Now here source is connected like this. So this is R2 that is equal to R02. Here it is connected. VG2 connected here. VG2 connected. So as usual everything is same, students. Here something enters A2 and again something is reflected B2. This is a 2-port network. So 2-port network. This is port 1. At port 1 whatever connected you have, that is called R1. That R1 is equal to terminating resistance at port 1. That means that is load impedance at port 1. R01 is reference impedance at port 1. And similar to this, this one is I2 and this one is V2 and this one is V1 here, like this, plus minus. Here R1 means terminating resistance at port 1 or otherwise load resistance. Now this is taken as this can be adjusted up to some resistance in such a way here reflected signal is 0. So here B1 is present, but there is no reflected signal. A1 is absent here because to define other parameters you need to maintain A1 0. To make A1 0, you adjust this resistance until this value becomes 0. So now here you can see that S12 is nothing but B1 by A2. So S12 is nothing but B1 by A2 provided A1 is equal to 0. For that purpose, to make that 0, we have taken reference impedance, we have taken what do you say, terminating impedance at port 1 is equal to reference impedance. Now this formula is similar to this one. 2 times of this side voltage divided by from where it is coming from VG2 and multiplied with this one R2 divided by R1 now. This is the exactly opposite of that one. Here 2V2 is there, right, V1. VG1, that means port 1 side you have connected the source. Now we have to connect at port 2 side, VG2. Now here R1 by R2, here R2 by R1. And once again, this formula itself came from derivation actually. इसको बहुत बड़ा derivation है. So this derivation is done by taking A2 0 by taking I will write here. So if A2 0 for that A1 0 na, for this A1 0, that means R1 is equal to R01 is taken. So this is the formula you have to remember. For this formula here. If you remember these two, and no need to remember them, just opposite to that you have to write. Similarly, S22 is equal to here B2 by A2. So B2 by A2. If A1 is equal to 0, for that you have to take terminating impedance at port 1, that means load impedance at port 1 is equal to reference impedance at port 1. That means you can change this resistance until you get A1 0. So that is the meaning of that. Because I am telling same thing so many times so that you will be comfortable with this. So here this is reflection coefficient at port 2. Actually this signal is sending the energy into the input terminal of the input terminal of port 2, so that impedance is Z2 minus of that energy is sending into the port 2 from the source having impedance R02, so that is R02 divided by Z2 plus ZL minus Z0 by ZL plus Z0 type this is. So here if A1 0 and R1 is equal to R0 1, here I will write dear students where Z1 is equal to this V1 by I1, V1 by I1, that is impedance, otherwise input impedance student, that is right now. So input impedance at port 1, that is input impedance at port 1. So similarly here where Z2 is equal to V2 by I2, that is nothing but input impedance at port 2. So now one method is there by taking defining B1 and A1. If you want, I will solve one problem based on that also. Another method is there by taking this formula and this formula doing the derivations. So whichever method is suitable for given case, it will be used like that. Now if you remember this is very simple. Reflection coefficient at port 1. This is nothing but transmission coefficient from port 1 to 2. So for that purpose, at port 1 you have connected voltage source. Then V2 means how much voltage is transferred to port 2. Then root of R1 by R2 is there, because going from port 1 to port 2, then 2 times is there. So if you remember these two, then exactly opposite of that you have to write here. Now we will solve some questions. Anyway, we will solve questions. After solving, you get S matrix. It is better you remember that S matrix, because in exam every time you can't solve them. Okay, so I will solve the questions.